All right, let's take a look at homework 6. So again, you got 3 problems. It involves polytropic boundary work, and the next 2 involve diving deep into the first law of a closed system. Okay, so if we look at problem 1, you have a piston cylinder device. It has nitrogen. It expands polytropically, and we want to find the boundary work. Okay, so it's nitrogen, so you can use the ideal gas equation. All right, mass is conserved between states. That's a good hint, right? It's always conserved. Remember, polytropic, this relationship between the states, PV to the N equals PV to the N for different states. You actually have to solve for N, okay? So I want you to try it. You can either do it mathematically, or I like to do it where I have an array of N's, and then I look to see when this side will equal that side. So I make an equation called left-hand side for this, right-hand side for this, and then I plot them as a function of my array N, and wherever they cross, right? That's when, so like if I plot left-hand side and right-hand side versus N, say this is left-hand side and say that's right-hand side, where they cross, that is your N. And then you can then go ahead and look back in the notes for the boundary work for a polytropic process. All right, so problem 2, you got a piston cylinder device. It's got saturated liquid, key word, right? Saturated liquid, constant pressure, okay? You got a paddle wheel, you got current. So you got to think of this piston cylinder device. It starts up. It could expand or it could contract depending on what's happening. So you have electric work, you have paddle wheel work, and you have boundary work, okay? So when you do these problems, you really need to clearly sketch your vapor dome. You need to clearly sketch your arrows in and out of the piston cylinder device for your energies. You got to then clearly write the first law out first, and then the next line down, cancel things that you don't need. Okay? And then break them down even more. For example, like big delta U could be M delta little u. Okay? Or in this case, I don't think it's not a gas, but you remember delta U could be Cp delta T if it's a superheat, okay? So make sure, or you could say H is U plus P over rho, or U plus P times V. There's times where you can break it down like that. And then once you have the equation broken down as far as you can go, look at your givens and then figure out what you need to find. You might have to find values on the table, which is why you draw the vapor dome, to figure out where you are. Are you a saturated mixture? Are you a saturated liquid? Are you a superheat? Okay. Now problem 3, again, uses the first law, but we have a spring attached to this. And it gives you steam at these pressures and volumes. We have a linear spring. All right, I want you to show the PV diagram, find the final temperature, the work done, and the total heat transfer. Okay, again, sketch the vapor dome, label your values, identify where you are initially and final. Okay, the reason I'm having you do a PV diagram is because the area under that graph gives you the boundary work. Okay, because work is the integral of PV in this case, okay, which is the area under the curve. So if you draw your vapor dome, you can find that area under those states, and that's your boundary work, which you will then use to find your heat transfer. Okay, again, write down your first law, break it down into the smallest components, figure out where you are on the states, find those in the table, plug them in. Okay, this should give you a very good starting point in this assignment. Good luck, and let me know if you have questions.